Hello everyone, I'm Lawrence from Extropy. Today I'm going to talk to you about zero-knowledge security and auditing zero-knowledge protocols and applications. These notes are available at that link, and there's a QR code there for you to find that link also. Okay, so what I want to talk about today, I will give you some background and features about zero-knowledge systems. We'll just quickly overview the major protocols in that space. Then we'll move on to looking at some of the common vulnerabilities that have been found. We'll have a quick overview of the tools. We'll talk about some of the aspects of auditing ZK systems, and then I'll give you some links where you can explore further. So, for background, a little bit of motivation. Well, zero-knowledge proofs are used very widely, particularly for ZK rollups, and we have many Layer 2 systems that are dependent upon ZK rollups, and they have a great deal of value locks. You can see here the TVL for some of the major projects. So there's a great deal of value involved in these systems, which makes them obviously potentially a very large target. Now, ZK generally is worth thinking about how it is used. So there are really two aspects, and sometimes you may think, well, it's all about computational integrity, and sometimes you think it's all about privacy. What I mean by computational integrity is that we can use it to prove that a particular computation has been done correctly. So with ZK rollups, we are showing that the execution of a transaction or a batch of transactions was done correctly on the layer 2. Privacy, this is another aspect that is sometimes used, sometimes not used. So we can have private inputs to computation, and the zero-knowledge proofs will preserve that privacy. But as I say, it's not always used. For example, on StarkNet, all the information is public, so they just kind of don't use that aspect. If you're new to ZK, the essential things you need to think about are that a ZK application or the protocol is an interaction between a prover and a verifier. So the prover has made some claim, and they want to create a proof that will convince the verifier that their claim is true. And so there's a process that we go through, and we check the claim in a certain way and do a number of transformations, which ends up with producing a proof. That proof is sent to the verifier, and the verifier then should be able to make a decision as to whether that proof is correct or not. The zero-knowledge aspect comes in that when the verifier has made that decision, they should only gain one piece of information, and that is whether the proof is correct or not. They shouldn't find out anything else, particularly if the prover had some secret information, some secret input to the computation. The verifier cannot find that out. Okay. Now, if you read about these systems and you see audit reports, we'll come on to this later, you'll see certain terminology, and there are some essential properties that a ZK system needs to have. The first one is called completeness, and this is the idea that if we have an honest prover and they supply a correct proof, then that will be accepted by the verifier. So this is really the everyday path, the happy path that the prover can create a proof, it's a correct proof, and that will be accepted. So the prover is very confident that if they are honest and they're creating a correct proof, it will be accepted. The second point, soundless, is really the reverse side of this, and this is trying to make sure that cheating cannot occur in the system. And so what we're saying is that a dishonest prover, if they create an incorrect proof, that is very unlikely to be accepted by an honest verifier. Now, this is probabilistic, so there is a chance that an incorrect proof would be accepted by an honest verifier, but this chance is extremely small, and so we tend to ignore it in practice. But we can get a bound on it. We can have an idea of what that probability is, and it is very small. Okay, and then the final essential property we have is the zero knowledginess, the fact that if there is some kind of private input to the computation or to the proof, that this cannot be found by the verifier. They cannot reverse engineer the proof or anything like that to find out what that secret input was. Okay. So the major way this has been used has been very widely used to help with scalability, and that's via ZK rollups or validity rollups in the Ethereum ecosystem, and those have been used to create the layer 2s, and of those we have a couple of major types. We have some that are compatible to some extent with the Ethereum virtual machine, and so these are known as the zkEVM protocols. So what they do is the execution on the layer 2 is done on something that is very similar to the EVM, and so hopefully you can use Solidity for that, and you can sort of easily port your existing projects to one of these zkEVM solutions. And then the execution of the transactions on this zkEVM is, we can create a proof of that, and then that proof is sent to the layer 1, where a verifier contract will check that it is being done correctly. The other types we have are layer 2s where the execution isn't trying to be compatible with the EVM. They're using some other type of execution, which is perfectly possible. There's, we can do that with ZK rollups, so there's no reason why we can't. But yes, they're not trying to be compatible with the EVM. On the ones that are trying to be compatible, we've got examples such as zkSync, Polygon, and Scroll. And then for the custom ones, we have StarkNet, for example, where they can use they have a Cairo VM. They use the Cairo language, which is completely separate to Solidity. There's no compatibility with the EVM at all. Also, Aztec, in the current version or the upcoming version of Aztec, is taking quite a different approach to execution. Although there is interaction with the EVM, they also have a thing called a private execution environment. So this is a little different as well. And then also we have protocols such as Mina. So this is not a layer 2. Mina is a layer 1. And again, there's no compatibility with the EVM. The programs are written in TypeScript and use a library called O1.js. And then RISC-0 is what is called a zkEVM. So it's just a general virtual machine. It doesn't necessarily have anything to do with blockchain, but it allows you to take any type of binary and create a proof that has been executed correctly. Okay, so these are some of the major protocols in the space at the moment. If application developers are developing for these systems, what they will tend to do, particularly with the more recent systems, is to write code in a domain-specific language, a higher-level language, such as Cairo, and or Noir for Aztec, and then this is compiled down into what is called a circuit. And yeah, we have some examples of these higher-level DSLs. A lot of them are based on Rust. They are very similar to Rust in terms of syntax and semantics, but not always. With Mina, for example, where they use TypeScript. And those then, these higher-level DSLs, they will compile down into these circuits. One of the another library that is used quite widely is called Circom, but this is a lower-level type of library. So it doesn't look like a traditional programming language. It doesn't look like Rust, and it is much more closely connected to the circuit. What you're writing in Circom is much more closely connected to this thing called a circuit. Now, the way that the proof is created is that, or the setup of the system, we have this DSL, and that will then compile into a circuit, or maybe you using Circom, and that will produce a circuit. This thing called a circuit is really a representation of checking the computation, and it's a transformation of the program that you have written, but it is transformed into something from which we can produce what are called constraints. So these are the checks in the system. So these are the checks that are checking that the claim that the prover makes is in fact correct. But the circuit is a representation in which we can more easily check it. And when we are creating a proof, we have to go through a number of transformations and get eventually to more mathematical representations of what the prover has been doing and the execution of the code. But the first part of that is called a circuit. And this language and the concepts about a circuit do intrude into the higher level languages. You do have to be aware of them. And when you are looking at the security of these protocols, there is a great emphasis on looking at this kind of representation, the circuit representation. Okay. Now, other aspects about zero knowledge that you should be aware of, it uses lots of cryptography. It is based upon things called finite fields. So these are mathematical objects. And so what we do in zero knowledge systems, rather than allowing ourselves free rein and using any types of numbers, we restrict the numbers that we use. So we use integers only, and we have integers that have a maximum value. So this is why the field is finite. And then we have modular arithmetic. So if you get up to the highest number and add one to that, then it will wrap around and you will start again at the beginning. So there is a finite number of integers available to you when you're doing computation that is going to be used to create a zero knowledge proof. Okay, and again, this aspect is important when we're looking at the circuits and we're looking how people are writing applications. You have to be aware of these facts. If we think about these systems in terms of what an attacker could achieve, as well as in addition to the usual types of attacks and motivations they would have with sort of Web3 applications, if you look at the ZK aspects in particular, one thing that they may be able to do would be to break privacy. And so that then this would mean that you think you have some kind of confidential computation, but in fact it isn't, and the attacker could find out some confidential information. The other thing that would be possible would be to create a false proof. So the prover has made some kind of claim, but they're actually cheating. They've created a false proof of this, but because of a flaw in the system, this would be accepted by the verifier. And to put this in more concrete terms, if we look at a project such as Zcash, the zero-knowledge proofs in Zcash are used to show that the transactions are being executed correctly and to show that invariants are being checked. So when we have a transfer of Zcash between two addresses, then the zero-knowledge proofs are there to prove that that is being done correctly, that we're not creating tokens out of thin air. So if we were able to create a false proof, what we could do would be to create tokens out of thin air, but then have it proof saying that that wasn't happening, to saying that things were working correctly. So this is the type of attack that will be possible if there's a flaw in the way that either the protocol is implemented or a particular application on that protocol is implemented. Another aspect to think about when we're thinking about ZK systems and applications is that I think that because of the very rigorous mathematics involved and the fact that these are called proofs and really the design of ZK proofs and what they can achieve, people are much more trusting of them, and they're therefore more likely to take risks in the applications. For example, if you have some a solidity contract and you claim that that is doing something, maybe you would check that, maybe you would be less likely to accept that immediately. Whereas if someone creates a proof that there's about some fact, I think you're more likely to believe that without further checking. So I think that in this way they are more powerful. They are more likely to be accepted, and therefore we may sort of take less security or use less security in these applications than we normally would. Also, one thing to bear in mind, and this is quite a difficult concept to come to terms with, but it's the way that we write these applications, is that the applications themselves are not really trying to compute some result, some answer. We're not trying to find a particular answer. It's more the case of we are taking some result provided by the prover, and then the application is there to make sure that that is correct and to prove that to check that claim. And in fact, to take that a little further, really the proof that we get is the proof that some computation happened, and that computation was there to check the claim that the prover is making. So there are some sort of logical steps that we make as we sort of go from the claim that the prover makes to the actual proof. And again, it is important to think about this because much of the potential problems we see in ZK applications are because we are not just checking sufficiently the claim that the prover is making. And so if we create a proof that these checks were run, that could be accepted. But if that would be a proof that a certain number of checks were run, but maybe those checks are insufficient. So this is one point we'll come on to in a moment, that the fact that the checks need to be rigorous, they need to be complete. Okay. Now, this next diagram, yes, it's a little complex, but I'll just quickly talk you through it to explain the typical process of how systems are set up and how proofs are created. And this is for a type of proving system called a SNARK, a zkSNARK. There are other types, such as STARKs, but this one is for SNARKs. It also applies pretty much to STARKs, but this is specific to SNARKs. So there are various aspects, but to start with, we have some kind of setup in our system, and that setup involves two parts. Part of it is taking the application and creating a circuit from that. So this is kind of the top path here. So maybe we would have some DSL that would be turned into a circuit. It could go into different representations, but that would be part of the setup. That's part of the process where we're showing to the verifier these are the checks that we're going to make about the prover's claim. So the verifier could well be involved in this initial setup. As well as that, for SNARKs, we have a thing called a CRS. Now, I won't go into details about this, but this is a special input that is needed. With SNARKs, we often have to have some secrecy around that as well. But this is all when you're setting up the system initially. The results of this setup are two pieces of data called the prover key and the verifier key. Now, these are not keys in the traditional sense, but they're really a summary of the setup of the system. And these are needed for the prover to create a proof and for the verifier to verify that proof. And they're really a summary of what the system is all about. Okay, so when once our system is set up, then we can create some proofs. So this is the part here, the public input and the private input. So the prover will be making some claim that could involve different types of inputs. There will be maybe some public ones, so these are inputs that the verifier can see. But there could be a private input as well, so that this is something that the verifier shouldn't know about. So the prover will have those inputs. They the private input is called the witness. So this is why we have this box called witness generation. So we have our inputs to the system, the inputs we're going to use as the basis of our proof. And we do this witness generation. The reason this has its own box here is because this part can be quite complex, particularly if the witness, for example, is the details of some program that is run, some execution. So, for example, on the layer 2 with the ZK rollups, the witness could be the execution that happened when one of these transactions was run on the system. So it can be quite a complex part. But either way, that is the witness. This would get sent to a prover, to something that is going to create the proof. The letters here we have X represents the public input, and W represents the private input, the witness. So the prover is taking the public and private inputs and sending those off to the SNARK prover, and that will create a proof. The public inputs can go directly to the verifier. So the SNARK prover is some process that will take the details and create a zero-knowledge proof from it. This proof here is represented by pi, and then the verifier will receive that. So the proof will be sent to the verifier along with any public inputs, plus the verification key, which is needed from the setup. Given all of that, the verifier will be able to decide whether the proof is correct or not. And then they may pass that information on to other applications. But the essential process really ends with the verifier making the decision whether the proof is correct or not. Okay. Now, where do we get problems? Well, this table is of a number of bugs that were found. They came from different places. You can see the audit reports, bug trackers, and disclosures. So you can break them down. If you look at the types of problems we see, what they broke, the majority of them have broken soundness. Some broke completeness, some broke zero knowledge. So if you go back to the points we have up here, the soundness being broken, this is the most common way that the zero knowledge systems will get broken. So what this means is that we are seeing the possibility that a dishonest prover could create a false proof, and then that would be accepted. So obviously that this is a serious thing to happen. Okay. The completeness, we're seeing that less. That just means that there's a possibility that a correct proof wouldn't be accepted. And then the zero knowledge part, this is to say that there was a leak, the privacy has leaked some way. And if you look at where these problems happened, the majority of them, as you can see, were in the circuit. The way that the circuit was written, whether that's because of the way it came from a DSL, or maybe it was from the Circom, a lower level way of writing circuits. But that the way of writing the circuit has got a flaw in it, and that's an area that we tend to concentrate on when we're auditing these types of systems. Okay. Now I'll take you through just a couple of examples. If you follow some of the links and look at some articles about this area, the majority of them, when they're showing vulnerabilities, they show vulnerabilities in Circom. So this is the low-level language. We are at a fairly early stage, and we haven't really seen enough examples in the domain-specific languages, in the higher-level languages. But I'll just take you through this. I appreciate you may be new to Circom, you may not understand how to read this, but this is an example of what is called an under-constraint circuit. Really, this is one of the major problems that you will see in this area. And the idea is that the prover has made some claim, and the circuit is there to check this claim. But the way the circuit has been written, we haven't been rigorous enough. We don't have sufficient checks in the circuit. And so this gives the prover some leeway. They could put in something incorrect, and it could still then go on to create a correct proof. And this in here we have problems because we are checking that something is, we want to check that something is the result of two factors being multiplied together, but we haven't specified it exactly as a constraint. We've just said that it's going to be equal, and also we haven't done checks on what these original factors are, because there could be edge cases where these factors would make a difference if they were certain values. So this general idea is the idea of under-constrained circuits is one of the major problems we see. And a subset of those are things called non-deterministic circuits. This is a little complex, but the idea then is that if you introduce some non-determinism into this area, then the prover again could take advantage of that. And so for certain circumstances, maybe they could create a proof that isn't sufficiently checked. Okay. A more straightforward example is given here with overflow or underflow. So this is really just because we're working with finite fields. We have a maximum value on that field. Typically, this would be a prime number. So here we've got it represented by P. So all of our arithmetic is going to be done mod P. And what you see here is that this line of code here is to say that we are adding three numbers together. We are going to put those three variables, x, y, and z. We're going to put those into variable a, and there's a constraint on that. So what we're saying is that a must be equal to x plus y plus z. But if we're not careful about how we do this, and we don't check the values of x, y, and z, then there are circumstances where we could get different inputs giving the same result. And so this is because we have overflow. So if you think of what we're going towards is that a is going to be equal to 11, what we have with these two examples is that there are different ways to get there. We've got, we could have x and y being 5 and 7, and then z being p minus 1. Or we could have x and y being 5 and 6, and z being 0, and these will both produce 11. Where we would typically we would want more constraints. We wouldn't want the case, the top case, where we could have effectively overflow. Okay, and this value p here, this is the maximum number in our finite field. So we haven't constrained this enough. We haven't checked the values of the individual elements sufficiently when we're doing this calculation. We haven't checked that z is within a certain range and is not going to cause overflow. Okay. So there's a good paper about vulnerabilities, a system of knowledge. So I've got a link to that there. Please have a look at that. There's also a nice article for safe circuits there to give you tips about those. Just to give you a further example, if you imagine we have our computation is going to involve some kind of accumulator, and what this accumulator is meant to be doing is as we step through the execution, at each step we're going to add 5 to the total. So you can see here in this table I've represented that we've got a column to represent the total, and then we've got one for the step. So the total here is increasing by 5 each time. So if you were writing constraints for this and writing a circuit for this to check that it was working correctly, you may just say, well, we're going to take the total of the previous row and add 5 to that, and then the total on this row has to be equal to that. And that certainly is a constraint, but then it's missing out other things. And I think application developers tend not to think in these terms. This is something of a new concept. They will write something such as total is the total of the previous row plus 5, because that's a way of computing the next row. But what we really need is a constraint about this. We're saying that the total on this row must be the total of the previous row plus 5. And then we need other constraints as well to say that this is being done correctly. So, for example, you should really say, well, what is the starting point? And that in the first step, our total must be 0. So that would be a constraint. Maybe you would have an ending point check as well, and saying what the total should be at the end. And then also you could have range checks to make sure that we, when we're adding these numbers, that we haven't got overflow or underflow. Overflow, I guess, because we're just adding. So you would be checking that the values that you are adding are within the correct range. So all of these are extra things that application developers may not initially think of, but which are very important. Okay. If you want some tools to help with this, there are some available. You can see here, this is just a little table to show you what they check for and how do they do that. Some of them are using formal verification, some static analysis, as you see here. And then they can check for under-constrained code, over-constrained code, or computational error. I haven't really mentioned these last two, but over-constrained code is really the opposite of the under-constrained. We tend not to see it as much, but it could still be a problem, because if you have too many constraints in your code, it could be that actually they're an honest prover with the correct inputs couldn't actually create a correct proof because the constraints are preventing them from doing that. So it's really quite a balancing act that you need to get, or for the application developer, to get the constraints correct. Okay, so going on to how we can audit these systems. So, of course, the usual points about Web3 and Web2 will apply. So there may be lots, for a particular application you're looking at, there may be lots of details that you would be checking around, the economics or just the general logic of the code, etc. So all of those things will still apply. But then in addition, we do have some extra things because this is a zero-knowledge system, because we are doing provable computation. Some of this is you're going to need very specialist knowledge to be able to check. So you're going to need a cryptographer to check some things, particularly if you're looking at the protocol level. There are things that that would require very specialist knowledge to understand. It may well be the case that you're going to assume that some things are working correctly. So, for example, you may have to assume that the compiler that takes the high-level code, the DSL, and turns that into a circuit, you may well assume that that is working correctly, which obviously could be incorrect, but then you would have to say in your report that this is one assumption that you are making. But the types of issues that someone without specialist knowledge may be able to find are things such as the under-constrained code. And this could be possible, this could be seen at the DSL level, because the application at the DSL level should be making sufficient checks about the claim that the prover is making. And so even at that level, you should be able to see if those checks are not sufficient, if you're not being rigorous enough. So this is the first point, where some things you can check without needing advanced cryptographic knowledge are things like under constraint code. Also things such as overflow. One aspect of the zero-knowledge applications that you tend to see is that in these languages, the data types are restricted in the maximum values you can have. We tend to have maximum values of around 2 to the 252. So they're often a little bit smaller than the maximum value we can get in Solidity. But when we're using these values, we need to be sure that we're not getting overflow. So there have to be checks on that as well. And then, of course, the breaking of privacy. If you have some secret inputs, you need to be sure that those are not being leaked in, or in some way maybe being reused in some way in the application that would make them visible to the verifier. Just to give you some examples of the types of checks that you can see, this is from the audit of Scroll, so one of the zkEVM protocols. done by Trail of Bits. So there's a link there to the audit. And these are some of the questions they asked as they were doing the audit. These are just a few of the questions they asked. If you want to look at the report, you'll see the full set. But it should give you an idea of some of the areas that you would need to look at. So the first one is, a more general one. Are we following best practices for Rust? Because they were writing in Rust. So obviously these are the traditional topics, the areas that you still need to check. But then also, because this is a zkEVM protocol, they wanted to check that really the compatibility of the EVM opcodes. Are they being correctly used? And then the circuits produced as part of the EVM implementation, are they sound and complete? And as you saw from the table of the types of problems that we see, we're probably going to be concentrating on the soundness aspect. The fact that making sure that a dishonest prover cannot create a false proof, and that will be accepted. There's more details here about the semantics of how the EVM works. So this is not really a ZK specific point, but it's just saying that we need to be checking that the EVM is correctly implemented. The point here of lookup tables, so lookup tables are a zero-knowledge feature. When we are writing circuits, one optimization that we can use is to introduce a thing called lookup table, where we put in some hard-coded values, and this is often more performant than trying to calculate something. But of course, if you do that, then you need to make sure that the values that are provided, these hard-coded values, are the correct ones, that they are in the correct range, that they are being used correctly, that a malicious prover couldn't somehow manipulate them to create a false proof. So there would need to be lots of constraints about those. This point here about the malicious prover, could they input some execution which would produce the same transition, but from different inputs? So this would be an example really of non-determinism within our circuit. So we would need to check that. Can the malicious prover convince a verifier that the state that has been reached by the EVM is different to what has actually happened? So again, this is really a mixture, I guess, of ZK, but also understanding how the EVM works. The way the constraints are built, so this is to do with the way that they are built and the circuit is created. Is that working correctly? Do we actually get the correct constraints in the circuit that we are expecting? Are opcodes working correctly? Are those when we that means not only is the opcode itself doing what it should be doing, but are we using the correct opcodes? Are we actually reading the bytecode correctly and stepping through the bytecode in the correct way? Of course, we should be looking at error states as well, whether that means that we have produced an error when we shouldn't, or we haven't produced an error when we should. We need to check that. This point here about the read-write table constraints and the memory constraints is to do with the memory part of the EVM. And when we use that and put items in memory, we do special, or we should be doing special checks to make sure that the item actually is within memory. When we have written it there, we need to make sure that it's been written correctly. Or if we're reading it, we need to make sure that has been read correctly. So there is a lot of rigor that has to go in when we're checking these applications, much more than you may expect when you're writing a traditional application. this next point, the Fiat-Shamir transformation, Fiat-Shamir is a heuristic that is used to take interactive proofs and make them non-interactive. And this is a common process that is used by all types of zero-knowledge proofs. This needs to be implemented correctly and securely, and there were certainly examples found where this hadn't been done, and again this would have allowed the prover to get an incorrect proof accepted by the verifier. So this is more maybe at the cryptography level and the protocol level, but there are guidelines around Fiat-Shamir to explain how it should be implemented, and there have been papers written to show where that was done incorrectly. So this next point is just a general one, though, yeah, we need soundness and completeness for our circuits. Also, if we have precompiled contracts, they obviously also need to work correctly and be complete and sound. So hopefully that gives you some idea of the types of things that were being checked in an audit of a ZK protocol. So just to finish off, if you would like to find out more, the Extropy, we run courses about auditing. We're going to run one this weekend. If you want to sign up for that, please follow this link here. Go to cryptoaudit.ninja and you can sign up for that. That course is quite practical. It concentrates more on Solidity and Ethereum. Rather, it's not specific to ZK, so it's more of a traditional audit course. But also as a company, we are auditors, and we audit mainly Solidity, but also Cairo, and we're about to start auditing Mina as well. So Mina have just introduced smart contracts, and we're going to see applications on their mainnet, so we're about to start auditing with them as well. There are details of our social media if you would like to get in touch with us. There's also an invite to our Discord server. If you join that, then you'll also get notifications when we create new courses or we have resources in this area. And the QR code there will bring you these notes. Okay, that's everything. I hope that was useful for you. I hope you enjoyed that. Thank you for your attention. I hope you have a good week, and I hope to speak to you all soon. Thank you. Bye-bye.